Welcome to Young Tuition. Let's continue discussing basic issues in atmospherical physics in relation to weather and climate phenomena. Today, I'm going to reconsider the textbook description about the atmospherical temperature and its vertical distributions in different atmospherical layers, namely troposphere, stratosphere, mesosphere, thermosphere, and so on. The reason I prepared this talk is that many take for granted concepts and ideas in this context would appear either meaningless or misleading. So, are you ready? Let's go and have fun. Temperature, heat, radiation, and energy are essential concepts in understanding weather and climate in relation to thermodynamics. When you listen to the daily weather forecast or have a chat with a stranger about the weather, are you sure you know what temperature is? Well, in fact, based on my teaching experience back in the 1980s, it would take several weeks for undergraduate students to understand temperature and related ideas in physics. By definition, the temperature of an object is proportional to the statistical mean value of kinetic energy of randomly moving particles, such as nitrogen and oxygen molecules in air at a thermal equilibrium. In this US standard atmosphere, it was loosely called the kinetic temperature. For gases, such kinetic temperature can be determined from this simple equation, namely, the mean kinetic energy of a molecule is equal to the product of the degree of its freedom, F, and half kT, where K is Boltzmann constant. For a point mass, the degree of freedom is 3. If we treat air near the surface as an ideal gas, which is made by many point mass particles, then we can calculate the air temperature simply from the measured air pressure and the mean air density, which is very accurate and independent of any radiation. By the way, this temperature is roughly the same as the subjective feeling by us, such as hot, warm, or cold. Why did I say roughly? Because human body is far from just a simple thermometer. Talking about a thermometer, I would mention a commonly used temperature sensor by experimental physicists, which is based on electrical resistance that is temperature dependent, such as this simple so-called thermocouple. The electrical potential difference can be easily measured and converted into temperature in Kelvin using an appropriate empirical formula. In fact, such electrical resistance-based thermometers have been extensively applied in measuring the atmospheric temperature distributions, as noticed in this US standard atmosphere. Nevertheless, the reading of this kind of thermometer becomes unreliable whenever the air density is too low to allow the frequent molecular conditions, which are essential to obtaining a mean kinetic energy. I mean the population mean value, statistically speaking. For this reason, each temperature curve in this diagram from many a textbook is obtained from multi-step averaged sample mean rather than true population mean. In other words, such vertical temperature distribution are just a guideline rather than the true mean atmospheric temperature distribution. Take 25 in the US standard atmosphere, for example, the range of the systematical variability of the atmospheric temperature increases with altitude, as you can see. That's why both the stratospheric cooling and the stratospheric warming have been reported from time to time. For Manabe and his followers, this is never-ending nightmare because their global warming theory is solely based on the stratospheric cooling. Perhaps you may ask, why don't we use an infrared thermometer such as this one instead? Good point. In fact, many instrumental observations have been based on radiation detection to determine the atmospheric temperature distributions remotely, either on the ground or from satellites. In this diagram, you can see a complete vertical temperature profile in the atmosphere from the sea level to over 500 kilometers, which is actually in space now, or the top of atmosphere. As you can see, the range of the variability is so big. It's over several hundred or even 1,000 Kelvin in the thermosphere. How come? That is because when you go as high as the thermosphere, there was not much air at all, except the radiation background, particularly from the sun. That variability is due to the effective solar radiation observable in the thermosphere. Perhaps you may ask why the temperature is so high over there. In order to understand why the temperature is so high at the top of atmosphere, you need to get familiar with another type of temperature used in physics called brightness temperature or emission temperature. And some people call it as radius temperature associated with radiation source. Unlike the kinetic temperature we discussed before, brightness temperature is defined in terms of radiation or electromagnetic wave intensity based on the Stefan-Boltzmann law. In other words, brightness temperature is not associated with molecular kinetic energy and conditions, but a phenomenological describer for how strong the radiation can be observed over there. To be more specific, you have to imagine the measured radiation is generated by an invisible black body whose surface equilibrium temperature is determined by the radiation intensity in watt per meter square. If you do want to attribute the radiation to a gray body, such as a thin layer in the atmosphere, as many climate researchers have done, then the brightness temperature would be higher. Why? For instance, the theoretical global mean value of the outgoing long-wave radiation should be close to 239 watt per meter square, as we discussed many times before. If you treat the planet with the atmosphere as a black body, then the brightness temperature or the emission temperature would be close to 255 Kelvin, which happens to be the kinetic temperature of the atmosphere at altitude 5 kilometers above the sea level, which is also called emission altitude by many researchers. However, the emission altitude can be quite different given the same outgoing long-wave radiation, because the atmosphere is not an ideal black body. You have to use an appropriate emissivity, say 0.8, in order to work out the true emission temperature. Do you agree? As a result, the actual temperature is 269 Kelvin, which is 14 Kelvin higher than 255 Kelvin. as shown in this diagram. How about the emission altitude? Well, it is now 2.9 kilometer rather than 5 kilometer. Confused? Never mind, me too, when I first look into such basic issues. Now I reckon over 97% climate researchers would be wrong if they cannot understand the difference I have just explained. I will discuss this issue in detail in the future. So, care must be taken whenever the atmospheric temperature above, say, the troposphere or lower parts of the stratosphere at most is to be used to predict long-term surface temperature, simply because these temperatures, no matter who had put them there, can hardly be determined accurately. This is understandable as the temperature distributions in the atmosphere are constantly changing because the solar radiation is periodic and non-uniform at the surface. Although some patterns could be recognized from time to time, such as the lapse rate and the ITCZ, the intertropical convergence zone, which I have been currently investigating. In short, the variation in stratospheric temperature distribution can hardly be used as a static reference for justifying the change in air temperature near the surface. Back in 1967, by way of contrast, Manabe and Witherald reported that they could use their calculated stratospheric cooling to explain the subsequent tropospheric and eventually the surface warming due to CO2 doubling, as shown in figure 16 in their paper. This has become the critical tunable parameter for all of general circulation models called GCMs, namely the model mean or ensemble mean surface temperature is always increasing forever. Remember, Gell-Mann called such an imagined imbalance as a circular term, which means frequency independent. That should be part of the basic determinant.
The random fluctuations, the cyclical behavior,
right?
Because the deniers talk about cycles, and they're right, there are cycles.
Yeah, sure.
And there are random terms.
Right.
And there is also the secular term.
Right.
But it seems he didn't do in-depth investigation on its origin. Just because he solved one of challenging puzzles in the standard model doesn't necessarily mean Gell-Mann was right on this issue. Instead, he seems irresponsible for saying so. How can I say so? Because I have quantitatively shown the prediction made by Manabe and Witherald in 1967 is incorrect. They concluded the initial stratospheric cooling due to CO2 doubling eventually causes the surface temperature warming. Instead, according to my calculation based on their result, stratospheric cooling actually implies the surface cooling. I will discuss this soon. Please stay tuned. Thank you for viewing. Thank you for donation. See you next time.